Hi there, sorry about that. I'm kind of using some new video kind of equipment and it kind of shorted on me. I kind of heard the beeping. But anyway, to continue back where I was, I'm saying that we can use this equation right here to then get our velocity final and start looking at some interesting trends. So our velocity final in our y equals -2 meters per second squared multiplied by our time, and we'll do the same thing again, time 1 through 4. 1 second. When we make it 1 second, VFY equals -2. Make it now 2 seconds. Becomes -4 meters per second. Then we have, make it 3. Then we get -6. Then make it 4. I think you see the trend here, but I want you to take a moment, go to Excel and try to graph this. And you'll see exactly why, when we have constant acceleration, so I'm going to erase all this now. I'm going to let you have one last chance to copy that down, or, I mean, why am I even giving that? You can rewind the video. But in any instance, what you can then do is go like this. If we know our A equals -2 meters per second squared, and we'll define this as our origin right here with, I'll define this as my origin right here, and we'll say that acceleration is on my dependent variable, my y-axis, t equals my x-axis, and I'm going to say that this point right here is equal to -2. If my -2 acceleration is consistent, we then, plotting this again, 1, and I know this isn't perfect, but bear with me. We can then say 1, 2, 3, 4. Straight line. Granted, I know that my artistic representations freehand are not great, but it's the idea. Then you go for your delta x, the final one. And then the delta x, we had same time over here. So if we had -2, oh, dang it, wait, never mind. That graph should be going in the negative direction. Alright, hold on. I'm gonna fix it. I done goofed. That's why we have to pay attention to our signs in physics. Actually, put this higher so people can see it better. Same trend though. Same exact idea. It's still representing the same acceleration, it's just shown in the form of velocity versus time. Then when we come over here, 1, 2, 3, 4 again, and I have to put this now on my negative axis because I'm being insanely ridiculous. Well, kind of ran out of space. One, 2, 3, 4. Then what were our values? 1, 4. It's like kind of hard to do it with here because I don't really have enough space. Actually, take a flash representation of this. See how this is linear right here. This is having a downward trend because it's going negative velocity. I just need the whole board to do this. Where's my... I have a ruler here somewhere. Ah, here it is. Handy dandy ruler. Okay. Now I'm going to set my my y-axis equals displacement, or delta y, displacement y, also known as delta x. Same concept, just, you know, kind of being a little pedantic with it, but we'll say that this is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Perfect. And then we'll make we have 12 from this point. Okay. 12 plus 8, we have 20. We'll make every 5 inches, say that that's equal to 1, that's equal to 2, that's equal to 3, and this guy out here is equal to 4. And we'll say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So here we are. Now comes the magic. So when we were at point 1, I'll do this in red, we had displaced 1 meter. When we were at point 2, we had gone 4 meters. When we were at point 3, we had gone 9 meters, so kind of hard to get this. When we were at point 4, we're down to 16. And what you see is a curve. You see that this thing is a little curve boy. It curves. And that's because the displacement is getting greater because the object's accelerating. So the faster you go, if you're inherently accelerating at a uniform rate, your velocity is going to increase uniformly in a line like this, and then your acceleration is going to remain constant. They're all saying the same thing. And I tied it back. Boom.